Okay, I want to talk a little bit about why calculus was invented. And really it's the story of this chap here. This is Sir Isaac Newton, lived a little while ago. Although, see this photo, it really could be anyone from that time. It really could be anyone. I mean, if you Google powdered wig, then you get this, and they all look like Isaac Newton. Anyway, Isaac Newton was kind of special because he had several laws of motion, and his second law of motion was that force is equal to mass of an object times the acceleration. So if we suppose that we're applying a constant force to an object and that the object has a constant mass, then the acceleration would be constant. Okay, so acceleration, if we imagine acceleration as a function of time, then it would kind of look like this. This is time. The acceleration would be constant. That's supposed to be a horizontal line, by the way. Now, if you've got constant acceleration, that means that the rate of change of velocity is constant. So the rate of change of velocity is dv dt. I should say standard notation, what we got here. A is acceleration. V is velocity. And S is displacement. This upsets some people that don't do physics because they think, hold on, why are you using S for displacement? Surely S is speed. No. In this context, S is displacement. Okay, so back to what I was saying. The rate of change of velocity with respect to time is equal to A, and we suppose that's a constant. If we suppose this is constant, then we can say that the integral of dv dt, the acceleration with respect to time, is equal to the integral of a dt, which is just a times t because a is a constant, and the integral of the derivative is the thing that you're differentiating back again. So that tells us that the velocity as a function of time is equal to a times t, all plus a constant of integration, of course. Now, what is this constant? Well, if you imagine that you're given some extra information, imagine we're talking about, we've got this cliff, and I'm at the top here of the cliff, and I'm about to throw my maths textbook off the cliff. Then, okay, I'm going to assume that I throw it in a horizontal fashion, and really I'm only interested in the vertical component of the velocity. And so if I throw it at time t equals 0, then the vertical component of velocity is 0. So v of 0 equals 0. And with this extra information, we can see that over here we'd need v of t is just a times t, because v of 0 would be a times 0 plus c, which means that c has got to be 0. Okay, so now we know what the velocity is. We could actually find out what the displacement is. So we could find we know the velocity at any time t, we can also find the displacement at any time t. So at this point t, we know that v of t is equal to at. Let me get this out of the way. need to make a bit of space here because it looks like it's t times v of t and it isn't. Okay, so there we go. At time t, the velocity is a times t. So we can integrate again because velocity is the rate of change of displacement. Now v of t is actually the rate of change ds dt, the rate of change of the displacement with respect to time, and that is equal to at. So now we integrate again. The integral of ds dt with respect to time should be the integral of at dt. And this isn't a hard integral. You can think of it as like a constant times x dx. So that'd be a t squared over 2 plus a constant of integration. And this integral here, the integral of derivative, is just the original function back again. So this is s at time t. Remember, this doesn't mean s times t, this means s at time t is equal to at squared over 2 plus c. So if we think of the displacement, the vertical displacement of my book being 0 at time 0, then this function s of t is equal to at squared over 2. Right, so all we need to know is well, what's the value of a? Turns out that for planet Earth, a is about 9.8 meters per second squared, which means that say 3 seconds after I throw my book off the cliff, I would find my book at s of 3, which is 9.8 times 3 squared over 2, which is about equal to, I need a calculator. .4 meters down, 44.1 meters down. So that distance there would be 44.1 meters. Now this is relevant to the work that I've set today for the SL. So have a look at that. This was exercise 10E that I set for the SL. We can see that here we have h of t looks like it's displacement and h dashed of t is 6t plus 1. We're told that h of 2 is 8. Okay, technically you can do this without even thinking of h of t as a displacement, but it's useful to think of it like that. Here, a particle moving in a straight line has velocity v meters per second and a displacement of s meters at time t seconds. The particle's velocity is given by v of t equals 4e to 2t plus t. Here, to find acceleration, you need to know that acceleration is the rate of change of velocity. So you would differentiate v with respect to t to find the acceleration. Anyway, I hope that's useful. Have a nice day.